Okay, so this is a video about modular congruence, and in this video I'm trying to give you the definition about modular congruence and some properties and some application about modular congruence. So why do we have to learn it? So I'll give you some applications for the modular congruence. So let's just begin with the definition. So, what is the meaning for being congruent? Well, actually, it's very related to divisibility. So let, for example, let m be a positive integer, and and um, we say that, for example, we have two numbers, or I should say two integers a and b. If we say they are congruence, so a congruence b modulo m, if the difference is in fact divisible by m. So that means a minus b is equal to k times m for some integer k. So that is the definition about why we have two numbers being congruent. Actually that means the difference has to be divisible by that positive integer m. So for example, so we have uh, 13 congruence to 2 modulo 11, for example. Why? Because since if you take the difference 13 minus 2, which is exactly 11, and it's clearly that the difference is a multiple of 11. Okay, so this is the very basic definition of two numbers being congruent with respect to some positive integer m. So what are the properties about congruence? So there are many properties actually. So in fact, many properties, you can find those properties from the notes, but let me just pick a few for discussion. So so number one, for example, if we have A congruence to B, for example, modulo M, and if we have another pair B congruence to C, let's say modulo the same integer M, then in fact we have A congruence to C modulo M as well. So we have this property. Now why do we have it? Well, actually the proof is very simple. So let me just give you the proof. Well, actually because A congruent to B modulo M and B congruent to C modulo M as well. So those two conditions are given. Okay, then we can use a definition. Then there are integers, for example k1 and k2, such that we have A minus B equal to k1 k1 times m, and also B minus C equals to k2 times m. So that is just the definition of congruence. Okay, now if we have these two, we can manipulate these two equations. Therefore, okay, so okay, A minus B. Okay, therefore we can have A minus C. You can just write it as A minus B plus B minus C. Okay, and that is just the sum of k1m plus k2m. And you can simply do a simple factorization and you get this expression. So you can see that a minus c is just a integer multiple of m. So by definition, we have a congruence to c modulo m as well. Okay, so that is the first property we have about congruence. So let's just do the other one. Okay, so maybe I just change it a little bit. Oh, okay. Oh, okay. Anyway, okay. So we have it, and then we have the number 2. Okay. So the second property is if we have a congruence to b modulo m. Okay, then actually we can multiply the relation by any other integer. That means we have a times c also congruence to b times c modulo m as well, and that is true for any integer, any positive integer c. So how do we prove it? So let's just prove it. Well, in fact, to prove it, we again apply the definition. So we have, because a congruence to b, so we have a minus b always equal to m times k. Okay, and for some integer k. So therefore, we can use this equation. For example, we can multiply that by any other integer c. We also have ac minus bc, which is equal to mkc. So actually, just like what I mentioned before, usually those definitions, they're not very useful. So the more useful thing you can use is equation. So therefore, you better translate all the definition, all the given condition to some equation. Then you can use the equation. So here we have AC minus BC equals to MKC, and because you can say you have KC times M. So KC, of course, is another integer. So that means you have AC minus BC just equal to a integer multiple of M, and we have AC congruence to BC modulo M. So we prove it. Okay, so actually those properties, you can see they are not very difficult. You just follow from the definition. So let's have another one. Okay, so let's have the third property. For example, if you have A congruence to B modulo M, and for example you have C congruent to D modulo M as well, well, what can you do? Well, actually you can sort of like multiplying the two equations together, you get AC equals to BD. So this is a very useful property in fact. Okay, and in fact we can use that to get another property which I will show you later, but let's see why this is true. Okay, so let me show you the proof as well. Well, again, in fact, you try to follow the definition and play around with those equations. So for example, you have A minus B equals to MK1, for example. and we have c minus d equal to mk2 as well, for some integers k1 and k2. So you if you don't like k1 and k2, you can use another name, but that is not very important. But we have a minus b and c minus d being an integer multiple of m. Now what can we do? So we can now remember what do we want to show? We want to show AC congruence to BD. Okay, that means you want to show the difference AC minus BD has to be a multiple of m. So this is what you want to want to prove. So that's why you try to take the difference. Okay, but well. Before you can really take the difference AC minus BD, well, of course, you have to, do some tricks. For example, you might have to add something and subtract something. Okay, so that something here is BC. Okay, so let's see why that is our our key for the problem. So you have AC minus BC. Okay, now this is just equal to MC. Oh, sorry. So equal to MCK1, and of course, if you think okay, you have a extra term BC, then the next equation, okay, for example, you use this equation, then you might have to multiply that by B. Okay, then you will have an extra BC. Okay, then you have BC minus BD equal to MBK2. Now you see, actually that BC, you can cancel the two BCs in the two equation. That means you just add them up and you will see something you want. Okay, so by adding the two equation, we have what? Well, for example, you have AC minus BC. Okay, let me just put a bracket and then add to BC minus BD. Then you add up the two difference, and because the BC just got cancelled, you have AC minus BD. Okay, but on the other hand, we also have, okay, we have this sum. Okay, in fact, it's nothing but just MCK1 plus MBK2, right? So you can do a factorization again, and you get CK1 plus BK2, okay, and that is, you multiply the sum to m. So now you see, actually, hence we have AC minus BD equal to exactly this this term, and therefore we have AC times AC congruence to BD by definition, because you just show that the difference is just a multiple of integer multiple of m. So we prove it. Okay, so that is a very useful property, saying that, well, you can sort of imagine they are just equation. So A equal to B and then C equal to D. You can multiply the two equations together to get what you want. Okay, but that's not the only thing you can use. In fact, you can do one more thing. Okay, for example, now that is a more useful property, I would say, because sooner or later I will show you some examples that in fact we can take powers, okay, on the congruence. Now this is the property that we will see. Okay, so for example, if we have A congruence to B modulo M, okay, and also, oh sorry, okay, A congruence to B modulo M, then what do we expect is actually we can raise it to any power. So we can have a to the power n also congruence to b to the power n modulo m. And that is true for any positive integer n. Okay? Now how do we prove it? In fact, the proof is not difficult because well, I can say actually this is one of the application of the property we just proved, the number 3 property. So the CY, okay, we apply, we use induction, okay, mathematical induction, okay. So it's a very good exercise for you to do the revision of on induction as well. So let's see why it is true. Now now you let, okay, so let, for example, you let Pn be the proposition, or you can say the statement, okay, to be what will be the statement that, okay, you have this, okay, be this statement, okay. Now how do you prove it? If you want to use induction, so you have to show, okay, when n equal to 1, what happened? Now when n equal to 1, a to the power 1 is just a, okay, but by definition, or but not by definition, but by the given condition, we know a must be congruent to b. So that's why you have a congruent to b, but b is just b to the power 1. So that means you have it trivially, okay, so it must be true, okay. So P1 is true, okay. Now if you want to use induction, then you have to assume or suppose P n is true for some integer k, okay. For example, you say n equal to k, okay. That means we have a to the power k equals to b to the power k modulo m, okay. Now the next thing you want to prove is you want to show that proposition is also true when n equal to k plus 1, right? So if you can do that, then you can then you're done, okay, because it's exactly mathematical induction. So how do we prove it? Well, now we have, okay, so now we have both, okay. We have a congruence to b modulo m, okay, modulo m, and also we have this, right? We both have it. So we can apply, so by property number 3, we just prove it, okay. We can use property number 3. So now how do we use it? Now because now for example, you have a congruent to b, and now let's say from property 3 you can take c equal to a to the power k, and for example you can take d equal to b to the power k. Then what you can get is this, okay. We have a times a to the power k, that will be congruent to b times b to the power k, okay. Exactly, you just apply property 3, okay. But of course you have to identify what are the variables, I mean what are c, what are d's, okay. So once you can identify those two numbers, well, it's just direct consequences of number 3. So now we have it. And so because you know a times a to the power k is just a to the power k plus 1, okay. So I use that symbol, okay, and that is exactly equal to b to the power k plus 1 as well, okay. It's just nothing but just the definition of index, okay. So we have it. Therefore we just prove pk plus 1 is true if, okay, so you have to say, so pk plus 1 is true if pk is true. Okay, so this is exactly the induction step. So once you finish, okay, so then by induction, Pn is true for all positive integer, n, I mean. Okay, so we prove property number 4. So that is very important, especially that allows you to take powers, and you will see later that we must use it in many examples. For example, we have a very large number in terms of some index, then how can you reduce the value by congruence? Actually, you must use property 3, because property 3 tells you that, well, if you raise it to some power, actually you still have the same relation. So we will see that, okay? And but I have to say that actually there are more property you can find. Okay, more properties on the nodes. So you can refer the properties on the nodes and see whether you understand the property or not. You can even try to prove it. Okay, they are not very difficult, and you can try to see if you understand or not.